Change of ideal gas entropy. Members:
Vances Cajusol José. Correa Bernal y Juliana. Flores Altamirano Cesia. Manaya y Sánchez José. Requejo Rodríguez Jacqueline. Ventura Monja Sozani. Engineer. Vera Lázaro Alejandro.
Contents: constant specific heat, approximate analysis, specific variable heat, exact analysis, isentropic processes of ideal gases, specific constant heat, specific variable heat. Introduction. Entropy is a thermodynamic method that indicates the degree of molecular disorder of a system. This can be created but not destroyed. It should be noted that there is a principle called entropy increase of the universe, which mentions that one of the possible final states of the universe is due to the fact that we will reach a maximum entropy, with which there will be no free energy for the processes that are performed on it. In other words, life on Earth will be completely finished. Change of ideal gas entropy. A formula for the entropy change of an ideal gas is obtained from equation 1, or 2. Substituting the derivative of U equal to the constant specific heat by the derivative of the temperature, and also, replace by the formula pressure equal to the specific R by the temperature divided by the volume in equation 1. Then we have the following formulas, derived from the is, that is equal to the derivative of the entropy on the temperature plus the pressure by the derivative of the volume on the temperature, that is the formula 1. We also have the formula, derived from is equal to the derivative of the enthalpy on the temperature plus the volume multiplied by the derivative of the pressure between the temperature, is the formula 2. By replacing, we will obtain that the derivative of S is equal to the specific heat of volume by the derivative of the temperature over the temperature plus the specific R by the derivative of the volume over the volume. The second relation for the entropy change of an ideal gas is obtained in a similar way to the previous one, substituting the derivative of the enthalpy equal to the specific heat of the pressure by the derivative of the temperature and the volume equal to the R specific by the temperature on the pressure in equation 2, and integrating. The result is, the entropy 2 minus the entropy 1 equals the integral of 1 to 2 by the specific heat of the volume by the temperature by the derivative of the temperature over the temperature itself plus the R specific by the natural logarithm of the volume 2 over the volume 1. It is considered to leave the expressed in this way because the specific heats of the ideal gases depend on the temperature and the integrals. It cannot be solved unless the dependence of the specific heat of the volume and the pressure with respect to the temperature is known. Therefore, two reasonable options are available: perform these integrations simply assuming constant specific heats, or evaluate them once and tabulate the results. Both approaches are presented below. When we would have the pressure, the procedure would be the same: specific constant heat, approximate analysis starting from the equations, the calculation expressions of ds for the function of temperature, pressure and volume of the initial and final states in a change of state are easily deduced. Then, integrating the expressions, the entropy variation between two states will be known. The equations obtained for both Cp and Cv are standard equations. The shaded expression, since P and T are the easiest variables to know in the industry for a fluid, table of average values of specific heats of air. This is a table of Cp and Cv of the air from which average values for the temperature are obtained. Entropy changes can also be expressed per unit mole, by multiplying these ratios by molar mass. The specific heat has units in the C of J/kgK. Its value, like that of C, is dependent on the temperature, and has a different value depending on whether it is a constant volume process, Cv, or a constant pressure, Cp. For solids and liquids, its value is usually tabulated at constant pressure, at atmospheric pressure, and at a given temperature. Variable specific heats. Exact analysis when the temperature change during a process is large and the specific heats of the ideal gas vary nonlinearly with the temperature range. The assumption of constant specific heats may lead to considerable errors in entropy change calculations. For those cases, the variation of specific heats with temperature should be properly accounted for by utilizing accurate relations for the specific heats as a function of temperature. The entropy change during a process is then determined by substituting these CVT, or CPT, relations into equation 731 or 732 and performing the integrations. Obviously, S degrees is a function of temperature alone, and its value is 0 at absolute zero temperature. The values of S degrees are calculated at various temperatures, and the results are tabulated in the appendix as a function of temperature for air. Given this definition, the integral in equation 732 becomes where is the value of at T2 and is the value at T1. Thus, it can also be expressed on a unit mole basis as. Note that unlike internal energy and enthalpy, the entropy of an ideal gas varies with specific volume or pressure as well as the temperature. Therefore, entropy cannot be tabulated as a function of temperature alone. The S degrees values in the tables account for the temperature dependence of entropy figure 733. The variation of entropy with pressure is accounted for by the last term in EQ 739. Another relation for entropy change can be developed based on equation 731, but this would require the definition of another function and tabulation of its values, which is not practical. Example: entropy change of an ideal gas. Air is compressed from an initial state of 100 kilopascals and 17 degrees Celsius to a final state of 600 kilopascals and 57 degrees Celsius. Determine the entropy change of air during this compression process by using A. property values from the air table and B. age specific heats. A. The properties of air are given in the air table, Table 17. Reading S degrees values at given temperatures and substituting, we find this equation. It is replaced in the aforementioned equation. A negative result is obtained. For the second part of the problem, I replace in the equation of the CP and with average value found per table in Poland we obtain a result similar to the previous one. This happens because the temperature is of a small value. If it had been large, the difference would have been used the previous equation. Isentropic processes of ideal gases. It is called isentropic process or isentropic, that reversible process, without the need to provide energy in the form of heat, then the process is isentropic. In this reversible process there is no heat exchange of the system with the environment, so it is said that the process is also adiabatic. Q equals 0. To make a reversible isentropic process, the system is thermally isolated, to prevent the exchange of heat with the environment, since many engineering systems, such as pumps, turbines and diffusers, are essentially adiabatic. They do not exchange heat with the medium. The second isentropic relation is obtained in a similar way from the equation, equating to 0. The equation that is obtained is, the second relation is the following. The third isentropic relation is obtained by replacing the first relation in the second, and we get the following equation. Generally, the ratio of specific heats K varies with temperature, so an average value K must be used for the given temperature range. And the isentropic relations of ideal gases are only valid for the isentropic processes of ideal gases. Specific variable heat. When the assumption of constant specific heats is not adequate, the isentropic relationships previously developed give results that are not sufficiently accurate. In such cases it is necessary to use an isentropic relationship that takes into account the variation of specific heats because of the temperature, that is the following. Whereas the value OS superscripto in T2 S superscripto 1 is the value in T1. By equating the equation to 0 you get, example, Helium gas is compressed by an adiabatic compressor from an initial state of 14 Celsius and 50 degrees Fahrenheit to a final temperature of 320 degrees Fahrenheit reversibly. Determine the helium exit pressure. By Table 8 the ratio of specific heat K of helium is 1667. Replacing in the formula we obtain the exit pressure, isentropic compression of the air in the motor of an automobile. Example. Air is compressed in a car engine at 22 degrees Celsius and 95 kilopascals in a reversible and adiabatic manner. If the compression ratio V1/V2 of the motor is 8, determine the final air temperature. Solution. Air is compressed entropically in a car engine. The final air temperature will be determined from a given compression ratio. We assume that under the specified conditions, air can be considered an ideal gas. Therefore, the isentropic relations for ideal gases are applicable. For closed systems we have this equation. As initial temperature we have T1 equals 295 K. To find the specific volume 1 to Table A17 ideal gas properties of air. And we get the specific volume 1. Then we clear and replace in the equation and get the specific volume 2. Getting V2. We go to Table A17 and we have to interpolate to get the temperature 2. Therefore, during this process the air temperature will increase 367.7 degrees K.